We know that from Q to R, this segment is called a chord. And we know if we were to label it on the side, we would write it as a segment. Segment QR is called a chord. We also know that PS, this segment right here, is a tangent if it were to keep going. But because it stops at points P and S and it doesn't keep going, we are more specific and call it a tangent segment. It is a tangent that is just a segment of a tangent, because normally we'd say a tangent is the entire line because the tangent keeps going. So we would also call PS a segment, but specify it as a tangent segment. Then we have a line that goes through the circle, intersecting at 2 points. Now I say a line because normally we see this type of line continuing in both directions and we call it a secant. But again, because it is just a segment, it starts and stops, or it has 2 endpoints, we call this a secant segment. And we can label it like we do the other ones. PR is a secant segment, segment PR. Then we have the segment that is just outside of the circle. I'm going to get rid of these dotted lines because I don't want you to think that they have to keep going. So we have this part that's sticking out of the circle right here from P to Q. Now because that doesn't actually go into the circle, we're not calling it a secant, and because it would not just touch at one point, if we were to extend it, we can't call it a tangent. So because it is outside the circle, but it is just a segment, we call it an external segment. So here you see we're using vocabulary that we already know, just applying it to more specific situations. Our goal, though, is to find lengths of segments. Let's begin with 2 chords intersecting, such as chord AB intersecting with chord AD at point E. Now, ultimately, what's important to remember when you have 2 chords intersecting is the formula that we use. Now, here's a chord from A to B. Here's another chord from C to D. When we want to find the lengths of any segments of these chords, or the entire chord, we use the formula that goes like this. AE, segment AE from A to E, times segment BE, so the other piece of this segment. So this half, well, it's not really a half, this part and this part multiplied to each other will equal, from the other chord, this part from C to E multiplied by this part from D to E. Ultimately, you want to have this formula memorized and know how to use it. So let's highlight it, star it, do something that's going to make it stand out to you so that you remember, yeah, we need to memorize this formula. Now, it may seem kind of arbitrary, where does this formula come from? So I'd like to show you. Now, it may be that putting this proof on your notes will make it a little bit cumbersome and perhaps a little bit more confusing than you'd prefer. So I'm going to go to a separate page, and if you'd like to draw this out with me, perhaps you draw it on just a blank piece of paper. Maybe you just sit back and watch. So here's the idea behind why that formula can be used. I'm going to take our chords and I'm going to connect from C to A and from B to D, and do you see what kind of shapes that I've made? That's right. 2 triangles, a triangle here and a triangle here. Let's mark some things we know about these 2 triangles. What do you know about these 2 triangles? Vertical angles, those are congruent. How about this inscribed angle, angle C? See how it's intercepting this arc right here? If you're not sure, I will trace the sides of angle C. It intercepts this arc right here. And I'll trace the sides of angle B. It goes into point A, it goes into point D, so it intercepts the same arc. So these two angles, angles C and angle B, are congruent to each other because they are inscribed angles intercepting the same arc. So what do you see now in this picture? Perhaps I make these two triangles bold. So there's triangle CAE and this other triangle BDE. Notice that here's one pair of congruent angles, here's another pair of congruent angles. When we have two pairs of congruent angles, it makes similar triangles. So by angle angle, we have similar triangles. And when we have similar triangles, that means we can make proportions relating the sides that are proportional. So how do we do that? Well, side CE right here. What side does this side correspond to? This side has the same marks as it. So CE and BE correspond to each other. I could write CE over BE equal to, so I started in the little triangle for that side and ended with the big triangle. What's another pair of sides that corresponds? How about this one? AE and DE. Those have the same markings, the single angle and the blank angle, so equals AE over DE. Well, how does that help us? How do we solve a proportion? We cross multiply. So AE times BE looks like this, equals, cross the other way, CE times DE. Look familiar? It should. That's the formula you just wrote down. AE times BE equals CE times DE. We got it from similar triangles. Now, do you want to have to make similar triangles every time? No, I didn't think so. So let's just memorize the formula. One thing I want you to notice about the formula is that that intersection point, point E, is in all parts of the formula. All of the segments touch that intersection point. Let's see how this works in some of our examples to find missing segment lengths. Find the value of x. Well, here's what I do. I see one of the chords and I take the pieces of it. X is one piece, 4 is the other piece. So I write 4 times x equals, then I look at the other chord. Here's the other chord. 3 is one of the pieces, 8 is the other piece. So I write 3 times 8. We multiply the pieces together, all of the pieces that touch that intersection point E. X touches it, 4 touches it, 3 touches it, 8 touches it. And then I solve the equation. 4 times x is 4x, 3 times 8, 24. Divide by 4, 24 divided by 4, 6. Would you like to try the next one on your own? Come back to the video. Here's one of the chords. Here's the intersection point. X is a piece, the other piece is x, so x times x equals, let's look at the other chord. 4 is a piece, 9 is a piece, so 4 times 9. X times x makes x squared. 4 times 9 makes 36. How do I make the squared go away? Square root of 36. Now I always, when I take the square root, consider positive or negative of the square root of 36. However, does it make sense to say x in this picture is a negative 6? No, it doesn't, because x is this length and x is this length. So just the positive value. Very good.